Aloha.
Aloha.
Thank you for attending this presentation of mine. My name is Dane Orton, and I'll be presenting my research on the temperature dependence of a diamine glucose fuel cell, also known as a glucose air alkaline fuel cell. Dr. Scott was my mentor helped me do this research, and it was done here at Brigham University. When I first got started, when I was first getting started on my research, I was really unsure of what I was going to do. I just chose Dr. Scott as a mentor, and then I told him I was interested in working with certain machines and equipment in the lab, specifically the potentiostat. And this is one of the potential research projects that I could have used. I could have done using the potentiostat. So basically, the search for sustainable energy is ongoing, specifically safe, cheap, and renewable energy. And there have also been some ways of harnessing energy that we can see every day in our automobiles, combustion of hydrocarbons in the combustion engine, as well as microbial fuel cells, which are not a commodity just yet, but it's in the development of. And finally, here at Brigham University, glucose fuel cell design was published in the past, and it uses a mediator dye to transport electrons from an oxidizable molecule such as glucose to the anode collecting surface. Now, to get started with running the glucose fuel cell, it requires 3 different constituents in the battery itself, and they all are added to one compartment because the reactions themselves don't produce any intermediates that interfere with the main reaction. So the stock solutions, I made a 3 molar glucose solution, a 10 molar potassium hydroxide solution, and then 20 millimolar of the dye. That's the concentration of the dye in the cell. And I mixed the dye with water and the glucose in one conical tube, and I put the KOH in a separate conical tube, because when you mix the base, it starts the reaction, and you want to start the reaction in the cell, in the apparatus. And all of these, those are all the reagents that are used. You can see the indocarmine and phylogen, blue and hydroquinone are the 4 dyes that were used. Okay, so this is the components of the glucose fuel cell. That's what it looks like. Those parts were just purchased right here at Ace Hardware and put together. The anode, the carbon-filled anode, and the MnO2 cathode were purchased online at Sigma Aldrich, I think, and as well as the dyes and the platinum wire. Now, at the top, as you can see, we have the carbon-filled anode, and at the bottom, we have the air-breathing cathode. It's called air-breathing because it's open to the air, and that's how oxygen is able to get in and get reduced for the fuel cell purpose. And the 3 components of the fuel cell is, like I mentioned, potassium hydroxide provides the alkaline environment. And 1 molar glucose, that's the oxidizable molecule, that's the fuel source, and then the dye. Now, the mechanism behind the fuel cell includes glucose being oxidized to gluconic acid. As oxygen is reduced at the cathode, it provides hydroxide ion, which makes the environment basic. And a basic environment causes glucose to be susceptible to attack by a mediator dye, and so it gets oxidized that way. The dye strips 2 electrons each per glucose molecule and transports those electrons to an anode surface. And those electrons are passed through an electronic circuit provided by the potentiostat. And electrons are passed back down to the cathode for another round of reduction of oxygen. This is the potentiostat which I mentioned before, which is used at the electronic circuit. Down at the bottom, you see the red and the blue wires. Those attach to the cathode and the anode. And this machine is hooked up to a computer to monitor as well. Now, the investigations for this research was to test the effects of temperature on the efficacy of the glucose fuel cell. And the experimental analysis consisted of running the experiment at 7 different temperatures, at 15, 19, 27, 32, 37, 42, and 49 degrees Celsius, with the exception of a 60 degrees Celsius run with chip and blue, and the dyes employed I mentioned before. Now the apparatus consists of the potentiostat right here, and then this is the oven. That's what controls the temperature. And the wires from the potentiostat goes into the apparatus, temperature apparatus here. The door closes so it maintains the constant temperature. And we use one of those things to monitor the temperature. So for each die, the voltage was monitored as the current was changed, and the current is manipulated using the potentiostat. And the voltage produced is indicative of the die that is being used. Each die had a different characteristic potential at each temperature, and each one of those lines represents a different temperature. Now from the potential, you multiply the potential by the current to get power. Now power is in units of milliwatts per centimeter squared, joules over area, and this is characteristic power curves at different temperatures for methodology. Now these two graphs that I just showed you, the potential and the power, was monitored for all 4 dyes, neocarmine, blue, and hydroquinone. I just haven't included those graphs in this presentation, but they were also monitored as well. After we get the power from the die, we made a temperature versus power curve, which shows how the power changes over a temperature range. And this is also done with every die. And those bars going up and down, those are error bars, and that corresponds to the standard deviations at each the standard deviations for the powers at each temperature. And this was the main result after having experimented with all 4 dyes. Their temperature versus power curves were overlaid, and as you can see, many things have happened here. First of all, indigo-carmine and methylbologen both produce the most power at a characteristic temperature of 32 degrees. However, indigo-carmine was able to hold this power for a longer duration, over a more broad temperature range, whereas methylbologen spikes really quickly at 32 and then goes back down. However, methylbologen did have a substantial power at 27 degrees, which is greater than all the other dyes. And Triple Blue had a very high power at 49 degrees, which is above all other dyes as well. However, after seeing how high of a power Triple Blue had at 49 degrees, I tried it at 60 degrees, but the power went back down to the same as it was at 50 degrees. Over the course of the temperature range for the hydroquinone and Triple Blue, from 15 degrees to about 37 degrees, their power actually increased by about 30 times. So my conclusions are, if you're going to use the glucose fuel cell, the selected dyes that you should use it with at 32 degrees Celsius is indigo-carmine methylbologen. The powers that they produced at 32 degrees Celsius were 2.31 milliwatts per centimeter squared and 2.39 milliwatts per centimeter squared. At 15 degrees, a lower temperature, these numbers are quite lower, about 8 times lower. And then if you're going to use the glucose fuel cell with the hydroquinone and Triple Blue as dyes, you might want to run it at a little higher, 37 degrees Celsius. And even though it doesn't give as much power as indigo-carmine methylbologen, it'll give as much power as it can, as the potential allows it to. Now Now, some issues encountered, just a couple things. First of all, with the temperature apparatus, you can see it uses a dial at the bottom to regulate the temperature. This wasn't the best way to regulate the temperature, in my opinion, because it was more like rounding off a temperature range, because the numbers on the dial only went up to like 10 or something, so it didn't tell you to set at exact 37 degrees Celsius. You set it to like 4, and then it jumped between like 32 and 39 sometimes. But that's the whole reason why we would wait 20 minutes before each experiment is run. So just to make sure the temperature is consistent as possible. And then the next issue was that cork on top of the fuel cell. Before we were just running it without the cork, and we were noticing the volume would drop due to evaporation. So that cork actually made it work really well. No volume was lost. And finally, my acknowledgments, I would really like to thank Brigham Young University for their resources and opportunity to do this research, as well as Dr. Scott for leading and guiding me in my research. And thank you for my fellow peers for your support and keeping me on track. And also, the results of this research are in the process of being published in the Journal of Power Sources, as it has been submitted a couple days ago. Dr. Scott is the main author of it, and my name is put on as the co-author of it. And thank you for listening.